Good morning, good afternoon, and good evening, wherever you are. Welcome to the APMP Time Zone online workshop on the SI in Fair Digital Data. I'm Thomas Liu, Senior Fellow at the Agency for Science, Technology and Research, and a faculty member of the ECE department at the National University of Singapore. I'm also a member of the International Committee of Weight and Measures. It is my pleasure to chair this presentation session on behalf of APMP today and tomorrow. With me is my co-host, Dr. Victoria Coleman, who is the section manager and project leader of the Nanometrology department at NMIA, and she's also the lead TC chair of APMP. In this online workshop, we hope you will have the opportunity to hear from and exchange ideas with leading experts and groups in digitalization related to metrology and data science, and perhaps take the first step towards establishing a basic standard for the digital SI framework. So this presentation session will discuss the importance of units of measure, the impact of digital transformation in the quality infrastructure, in the regional metrology organization, and in industrial infrastructure, and how to ensure metrological services are suitable for the digital future, as well as the opportunities for the user community to tap on these new capabilities. There are 5 topics to be covered in these 2 days, 2 for today and 3 for tomorrow. Benjamin, do I see the slides? All right, okay, sorry. So the presentation are pre-recorded. You may submit your questions and discussion points through the chat function when the presentations are being played, right? The questions will be addressed during the discussion part of the program. In the case of talks where no representative is available at the live discussion, the question will be forwarded to the speakers. So please do indicate the name of the speaker you want to have the question addressed. So today, our first topic is on global data science, and there will be 3 presentations. The first one is by Dr. Simon Cox. Dr. Cox works on practices and standards for the publication and transfer of science data, particularly geospatial data. After starting his career in geophysics and mine exploration, with the emergence of the World Wide Web, he became involved in data and informatics. He is principal and co-author of a number of international standards for data. His current focus is on fair data, link open data, and semantic web technology, with a particular emphasis on formalization, publication, and maintenance of control vocabularies and related reference data. He's a member of the Standards Australia Committee IT 004 on Geographic Information, the National Committee on Data in Science, and is the executive committee member of the Committee on Data or CODATA of the International Science Council. Our second speaker today is Eric Schütters. Dr. Eric Schütters is the International Science Coordinator at GoFair, International Support and Coordination Office. He is also a member of the Leiden Center for Data Science. In recent years, Eric has been working with a diverse community of stakeholders to develop fair data and services within and outside of the life sciences. And our third speaker for this morning is Miss Sarah Jones. Sarah has worked in the field of open science and research data management for the past decade. Previously, she was Associate Director at the Digital Curation Center, and in July 2020, she began at GIAN as European Open Science Cloud Engagement Manager. She has been involved in several European Commission funded projects such as EUDAT, OpenAIRE, FAIR's FAIR, work on expert group for fair data and a transport research cloud, and was an independent expert at the EOSC Executive Board. For RDA, she is co-chair of two groups, Active Data Management Plans Interest Group, and Global Open Research Common Interest Group. So without further ado, we will start the program today with the playing of the recorded presentation. Yep, Benjamin.
Hello, I'm Simon Cox from CSIRO, which is Australia's National Applied Research Organisation. My presentation is on digital units of measure services, communities, coverage, and alignment. So here's an outline of what I'll be telling you about today. I'll be introducing and reviewing a number of existing digital units of measure systems. Why is there more than one? Well, this is related to their origins in different communities and different applications who have different interests and scope. Also, there have been a few different technologies and different levels of adoption, both within and outside the originating community. Finally, I'll make some comments on the potential for harmonization and what is already going on in alignments. Why is this relevant to digital SI? Well, I guess this should be obvious, but just in case, SI is just a subset of all the units of measure that are in use. It is the most important rational subset and is almost always used as the bridge between other systems, such that pretty much all other systems of units, even in the US now, are now defined as scaled versions of SI. There are also many existing digital machine-readable units of measure representations. To understand if we can make use of them, we need first to understand a bit about their scope and technology, and importantly, where they come from, which applications and communities built them. I'm going to describe three systems in detail and then summarize several more. First off, the Unified Code for Units of Measure, or UCUM. UCUM is an implementation of and direct successor to a series of standards that aimed to define codes for units of measure that, on the one hand, look like the usual scientific codes, but on the other hand, can be typed on a standard keyboard. Some of you will recognize the names of the predecessors. None of these was complete or fully consistent, so starting in 1998, EUCUM has attempted to rationalize them. It is primarily the work of two heroic souls, Gunther Schadow and Clem MacDonald, and is formally owned by the Regenstrief Institute, which, despite its odd name, is part of the US National Library of Medicine. Here's the summary of what EUCUM does. Note that the symbols that are not available on a standard keyboard are approximated. The base symbols can be combined with prefixes for compound or multiple units, for example, decagray and femtomole, milliliter, centimeter, or by multiplying or dividing them or raising them to integer powers for derived units. Non-SI terminals are also available, for example, colony-forming units, percent, gray. Qualifier suffixes are in square brackets, for example, centimeters of mercury, and annotation suffixes, which don't actually change the values, the conversion factors, are in braces, e.g., for example, percent volume. The definitions table includes the conversion factor 2SI for each atom, which allows any quantity scaled with a valid EUCUM code to be converted. The formal definition of EUCUM is a Backus-Naur production rule, which can be implemented using the finite state machine shown on the right. The EUCUM dataset is an XML document. You can see the small amount of detail required for each definition here. As I mentioned previously, EUCUM comes from the health and clinical medicine application space. EUCUM is built into HL7's FHIR system, which is widely used in clinical settings. There are also some validation and quantities conversion services available. There I've shown both the user interface and the service descriptions. EUCUM is considered essentially complete, but there is a public maintenance process managed through a track ticketing system. Fixes and enhancements are still occasionally made, but note that because EUCUM defines a generative algorithm for derived units, it does not require an update or new release just to add a new derived unit code, which only uses existing atoms. Next, the QUDT, Quantities, Units, Dimensions and Types system, originally from NASA and Top Quadrant. QUDT actually came about following the issues with units that contributed to the Mars lander accident. QUDT now has its own organization, though Top Quadrant still supports it. The QUDT model links units to quantity kinds to give the semantics and dimension vectors to give the physics, if you like, within the systems. This diagram is just to give a sense of the level of detail that is supported by QUDT, as it also includes recording the symbols and codes from various symbol systems, including LaTeX, UNECE, and EUCUM, and also offsets and multipliers relative to SI required for conversions. QUDT publishes a series of collections, one for each type from the model. So there is a set of quantity kinds, a set of dimension vectors, and a set of actual units, as well as these other pieces. Here's the top of the units catalog, showing the A's. Symbols like unit : A-per-M are shorthand for URIs, which are persistent web identifiers. The actual URI for that unit I just read out is shown at the top of this example entry, and the whole entry shows the detail available for each entry, including the EUCUM code. QUDT is implemented in AL2 and also in Shackle. Maintenance is tracked in a public GitHub repository. New releases occur approximately monthly, typically with 1 to 10 new units, plus other fixes. QUDT came from engineering applications and has been adopted in a number of engineering and manufacturing contexts, as well as some science areas. The NERC vocabulary service includes one collection of units of measure, known as P06. The NERC vocabulary service, or NVS, is a big vocabulary service which is an important part of the marine science and oceanography infrastructure. The oceans community tends to be quite good at establishing and maintaining shared infrastructure, probably because their kit is big and expensive, therefore usually shared. We're talking about ships and global constellations of sensor platforms. NVS has around 300 separate vocabularies, of which P06 is just one. Some of these vocabularies are very large. For example, the notorious P01 has around 50,000 terms in it. P06 is essentially an inventory of units that are used in actual data sets. It is not designed to be fundamental or comprehensive, so there are sometimes surprising omissions. For example, P06 includes knots, nautical miles per hour, but nautical miles is not there because no data sets measure distance in nautical miles. Here is one of the entries from P06. A key point here is that it is not a fully structured unit definition, just a name, identifier, and textual description, together with a large set of links to related terms in other NVS vocabularies, mostly to terms in the observable properties inventory, that is the quantity kinds that use this unit. The simplicity of the representation is because this collection of terms is formalized in SCOS. SCOS is the standard formalization of all the definitions of NVS. And here's the SCOS serialization of becquerels per kilogram. Note that there is also a link to the QUDT definition, so a formal structured definition could be got to from here. As mentioned, NVS comes from the international marine science and oceanography community. It is comprehensively used in operational systems within that community, particularly by the European members. But NVS is also used as a reference point for definitions by the entire international Earth and environment science community. So that was an overview of 3 of the key systems for digital representation of units of measurement. Each of the ones I showed has got quite a long heritage and also significant adoption and implementation in one or other community. EUCOM in health and clinical medicine, particularly in HL7 fire, QUDT in engineering and science, and NVS P06 in marine science and oceanography. However, there are a few other systems that are worth mentioning. OM, UO, and SWEET are all OWL ontologies. They come from science communities. While they're not necessarily implemented in operational systems, they are the basis of a lot of analysis and investigation amongst ontologists and in experimental systems supporting science data. OM is hosted at Wageningen. UO is part of the Open Biomedical Ontologies, or OBO Foundry. And SWEET was originally also developed at NASA, but is now maintained by the Earth Science Information Partners, which is funded through NASA, NOAA, and the USGS. Moving on to a bit of analysis and consideration of why so many, and is there anything to be done about it? First, some statistics. Here I've just counted the number of units in each system, plus a few other types where I think they are interesting. UCOM is in principle the most parsimonious, as it only has the unit atoms that can then be combined to build an unlimited set of derived units, but there are still 310 entries. QUDT is the biggest in this survey at 1700. However, 350 of these units are either currencies, oh dear, or multiples or submultiples of simple units. QUDT also has substantial catalogues of more than 800 quantity kinds and around 200 dimension vectors. OM has almost as many units as QUDT with more than 1400, but as well as currencies, yikes again, it also includes a lot more multiples and submultiples, since it exhaustively enumerates all the petas and yotas and attos and femtos and yoctos of many basic units, even though they would rarely, if ever, be seen or used. Suite is just an inventory of 138 units that the editors had come across in Earth Science. And similarly, P06 is an inventory of 375 units that appear in marine data sets. Finally, UO is a set of 597 units from biomedicine. Surely these could be replaced by one system. Well, yes, the theory to describe a unit of measurement is straightforward, and the models show the same classes, sometimes with slightly different names, but are easy to transform. However, the prospect of harmonization to a single system, I don't see that as practical or necessarily even desirable to imagine that the systems can be replaced anytime soon. Some of them are built into big operational systems with a significant investment, and they work well enough, so why would the operators replace them? However, there is definitely no need for any new systems, so we need to advertise the existence of these. And as long as we can keep the numbers down, fewer than 10 say, then one-to-one mappings between them can probably be maintained. And there has been some progress on alignment. There are now mappings from all of the systems to UCOM and from several of them to QUDT. I've been involved in building many of these mappings. The rationale for using UCOM and QUDT as the core for alignments is that the UCOM codes are unique textual identifiers, so can be used as keys for joins. And QUDT, having a full semantic model, able to describe derived units as well as the fundamental ones, and is also the most responsive to update requests. Adding a new unit, or addition of a new unit, can be processed in a few days, and there is a formal release of QUDT round about monthly. So what have I told you? There are a number of existing systems for digital descriptions of units of measurement with various levels of modeling and formality. Most of these are potentially fully general, though the exact inventory and implementation in each are grounded in a specific community. UCOM being purely generative, while the others each persist an essentially arbitrary suite of derived units representing an inventory of units used in a suite of applications within the specified community. There are some alignment efforts underway, primarily based on using UCOM as the textual key and QUDT for rapid publication of U units for bridging purposes. I think that's probably enough for now. I'm done. Thank you.
Hello, my name is Eric Schultes. I'm the FAIR Implementation Coordinator at the Go FAIR Foundation here in Leiden, the Netherlands. And I'm very happy to be with you today at the FAIR Systems of Units conference and workshop. And I would like to tell you today about recent work we've done on making FAIR metadata and making it easy for people to make FAIR metadata, and our interest in incorporating FAIR SI into the work that we're doing. And this is, by the way, all in the context of the Dutch COVID-19 research program. So this is really work that's been built up in a very urgent way over the last year. And so I'll try and take you through that process and see how we are trying to focus in on FAIR system of units. And before we get into the details, I want to certainly acknowledge the hard work and the great efforts of a team of people that are working to create an easy pathway for domain experts to create the metadata that they need to express their data in increasingly fair ways. And I want to highlight in particular the work of Barbara and Nicola, whose work I will draw on pretty heavily in this presentation. And I also wanted to mention that the work that I'm presenting, although very focused in a use case on COVID-19 in a Dutch setting, is actually part of a much larger FAIRification framework. And I won't go into details on this today, but I have a link here so you can see that the things we're trying to do with metadata actually fit into a larger FAIRification framework. So let's begin with the COVID-19 data portal project. So this is a national research program in the Netherlands, launched in urgency with lightning speed to research and make progress on COVID-19 related issues. There's two notable characteristics about this funding program that are quite extraordinary, quite innovative. The first is that there's a mandate within the ZonMV research program that research outputs are to be made fair. So that's a pretty strong mandate, but it's backed up by, number two, the support for fair data stewardship, both at the level of the PI. So that's this, I mentioned here, this 5% discretionary budget available to the PI for fair data stewardship issues. But then there's a larger project in the background that's working to create tools and services and methods that enable fair data stewardship. And I have a quotation here by Margreet Bloemer, who's the architect of this COVID-19 research program. And so to get into the content here, it's very nice to focus at the beginning on the FAIR principles themselves. And what you see immediately when you look at the principles is that metadata is everywhere. And I think the FAIR principles have done a great job elevating the idea of metadata to be really a first-class citizen with the data itself. And just in December, both Mark Wilkinson and Mark Mewson had independently mentioned to me that FAIR is 90% metadata. And so I asked them if I could use this quote, and they said, sure, go ahead. So from these experts, we can see that metadata is in fact gonna take us a long way down the road to fairness. I also wanted to highlight principle R 1.3, which asks us to focus on domain relevant community standards for both data and metadata. And this is what really inspired and took us into this idea of metadata for machine workshops. Because although domain experts are required to create their domain relevant community standards, in most domains, most experts are probably not experts themselves in metadata, and maybe not, or certainly not in most cases, are they experts in machine actionable metadata. So the metadata for machine workshop idea was to say, well, if we want increasingly for domain experts to use and to create fair metadata, then we probably need to team them up with experts in FAIR metadata. And in a kind of hackathon environment, they could be able to produce the vocabularies and the metadata schema that are required to lift their data assets to a very high level of fairness. And what that means is that these metadata components are themselves fair at a technical level, that they fulfill the domain-specific requirements. And we know that's the case because we have the domain expert in the workshop, and that these outputs, these vocabularies and metadata schema are themselves reusable. And we think if that's the case, if these three conditions hold, then we should be able to see the creation and then the widespread adoption and reuse of useful FAIR metadata components. And in this workshop environment over the last couple of years, we've drawn on several different tooling and in research groups that have been working to perfect methods in FAIR metadata. And I'll show how that looks in the presentation. And what I want to mention today is that we'd like to try and get to FAIR SI units as a part of our work in metadata for machine workshops. And for this, we're looking at the moment at the QDT standards, and I'll show you how that looks. So the metadata for machine workshops that we launched for the ZoneMV COVID program began last September, October, and it was really in November that we launched 6 metadata for machine workshops. We distributed the 62 research projects in the COVID program over these workshops. And you can see them listed there in terms of the number of people, number of projects. And in each case, in these workshops in November, we had the research domain experts and a data steward help us brainstorm on what we call project assets. So anything related to the project that needed to be described by metadata, such as data, biomaterials, services, standards, we went through very controlled, very structured brainstorm sessions using a tool called Padlet. This was all done online, of course. And what this allowed us to do is pull out of the domain expert the preferred terminologies that describe their research assets. And now what we've done in February is we've run an additional couple of workshops where we've been able to consolidate that list of terminologies, and we've begun building a formal vocabulary that describes these things. And in this, we've been linking to the existing vocabularies in BioPortal ontology repository. And we've been using tooling that we've developed in what's called the FAIR Data Collective. And the ultimate goal here is to produce a COVID-19 research program vocabulary agreed upon by all 62 research projects, and that vocabulary would be available then for the CDAR workbench, which is a very nice tool that allows you to compose metadata templates in kind of a modular format. And then these templates become shareable as simple web forms or through APIs. And then either machines or humans can populate these templates and create metadata instances for different data sets, for different projects, et cetera. And what we will ask the data stewards in the COVID program, our Dutch data stewards, we will ask them to work closely in support of the researchers to help get these forms more and more routinely filled in, and thus creating metadata assets for the research project. And these metadata and the data themselves will then be put onto a network of FAIR data points and made available in a fair way. That's the COVID-19 research program, and this is some of the tooling we're using to try and create reusable metadata components. And I just wanted to mention, though, that above and beyond this one instance of COVID-19 research for ZoneMV, there are other metadata for machine workshops that we're running, some of them COVID related. And so you can begin to see that there should be automatically now a great deal of overlap that we can reuse vocabulary and templates from previous metadata for machine workshops. But it may be surprising for some that we can even reuse quite heavily components that are created in completely different domains. So for example, with the Danish group, we've run metadata for machine workshops 5 and 6 based on wind energy data sets. And in fact, we are repurposing quite heavily from wind energy domain in the COVID domain. But this is all in an effort to try and to get reusable metadata components and to not have to reinvent the wheel each time. And by using these components, we can better guarantee interoperability and fairness. So coming back then to these metadata templates that we created as part of the COVID-19 program during November and February, there's really 3 templates here that we have. We call it at the top, you see the project administrative metadata template. In the middle is the project content metadata template. And at the bottom is the generic dataset metadata template. These are links to the templates themselves. As you can imagine, the project admin metadata is just very high level. I think there's 22 fields that are requesting very basic information about the project. So the PIs, the funding agency, the grant number, et cetera. The content metadata template in the middle is starting to give an overview of the scientific content of the research project itself. But again, at a very high level. But that project content metadata could point to data set metadata so that we have a quite extensive template for any data set that might be created in the course of these research projects. And I want to zoom in on this, on the generic data set metadata template. And you can see for yourself at this link at the top at OpenView. But you can see here a bunch of fields. I think there's 90 fields total, although a very small number like 10 or 12 are required. But you can see these are general types of fields that can describe and be applicable to any kind of data set. And I want to highlight then this one particular field called variable. And this is a very modular component of the metadata template that basically asks, what did you measure? Describe that measurement you made. And although we have a model behind this now, it's very straightforward, very simple. As the iAdopt group at RDA finishes its work on creating a more elaborate data model for what they call observable properties, we will almost certainly be using this as well. Here's a deeper view of the iAdopt observable properties. And so what you can see is that the observable property, so the thing that you're measuring, can be characterized by observed object, observed property of that object. And there's modifiers, including measurements and units and units of measure. And we will be extending, or let's say adopting vocabularies for this model from the QDT unit and QDT quantity kind vocabulary. And so here's an example of a generic dataset metadata template. This is a CDAR template. And in this case, this is for a COVID-related measurement, like average physical exercise duration per day. We are observing time. This is for physical exercise for humans. This is measured per day. We're looking at the average, and our unit of measure is an hour. And we will take that unit of measure description from the QDT vocabulary. And so what you can see then is that this CDAR form is going to contain within it drop-down menus that allow the researcher to be able to select from fair or verified units of measure in a very direct way, helping to structure and make machine readable the metadata that's being input. Here's some other observable properties in the COVID program. that we've procured from our data stewards. And the hope here is that we will be able to embed in these CDAR metadata templates QDT units for a range of different measurements, like concentration of virus and saliva, blood pressure readings, weight, length, body mass index, etc. And once we have these templates, then the exciting part is that we are able to then repurpose these templates and the vocabularies that they're using for other projects and other research domains. And so, for example, the Wellcome Trust and ZoneMV are now committing to the next generation of metadata for machine workshops, not only in the COVID space, but in other biomedical and research domains. This is also true for the Danish E-Infrastructure Corporation. There's a metadata for machine workshop in April on bioimaging. We will have another workshop later in the spring on carbon credit technology. And then the Health Research Board of Ireland is also now more interested in running a metadata for machine workshop for COVID-related topics. And the idea here is that what we would like to do is have reusable metadata templates that are using these FAIR units of measure, and that are becoming more and more mandated in their use by the funding agencies themselves. And we hope that this combination of these CDAR templates with the funders in these research projects will help to further the uptake and the widespread use of FAIR system of units in the future. Thank you.
Hi, I'm Sarah Jones from Géant, and I've been asked to speak to you about the EOSC interoperability framework and how that's facilitating cross-domain discovery and reuse in the European context. So first off, I wanted to explain a little about what EOSC is. So EOSC stands for the European Open Science Cloud, and it's an initiative led by the European Commission, which is creating a web of FAIR data and services. So what we're doing is federating the different e-infrastructure and research infrastructures across Europe to provide an environment in which data can be brought together with all the services to perform the analysis and enable researchers to address societal challenges because they can get all the relevant data from the different spaces. So you can see in the visual on the right here, the basic kind of architecture of EOSC. We have a core set of services, so things around AAI, so authentication and access, around the persistent identifiers and metrics and help desk services. And then what we're doing is federating both data from different repositories and different communities. And we have this EOSC exchange layer where a range of other resources and services are brought together to enable researchers to choose those to act on those data sets. So the aim of EOSC is to enable multidisciplinary discovery and reuse. At the moment, we have a number of research clusters and infrastructures, and if researchers want to use data from other spaces, they'll need to consult with services and repositories in different areas and bring the data together manually. And the EOSC vision is to federate these disconnected silos so that we can have one environment in which researchers are able to find all the relevant data and then to act on that as well. And this is part of a broader vision. The EC is signing a number of European partnerships at the moment and investing in a number of data spaces. So in the areas of agricultural data, for example, or energy or the Green Deal. And EOSC is a horizontal that cuts across these, that's addressing all different research communities, and we're aligning with these different data spaces. So what I want to focus on in this presentation is the interoperability framework. This is something that's been developed through the current EOS governance. There are a series of working groups that were established, and the architecture and the FAIR working groups came together to develop the interoperability framework. And you can see how this fits into that overall model of EOSC, and that it's really a layer to help us bring together all the different types of output, so not just data, but publications, software, and services, and to interoperate between those. The interoperability framework has FAIR at its core, so this is a key concept for EOSC. We want to make sure that all the objects within EOSC are fair, that we can discover them, we understand the permissions that are assigned to those, and they're conforming to community standards so that we're able to reuse. So this is a kind of core premise that runs through the interoperability framework. The main report has been published and is now available on the EC's portal. And you've got the DOI there, so you can go and download that. And there are a couple of additional files that we made available. One of the things that came back when we consulted on the initial recommendations was the need to develop a reference architecture. Now, the group that was doing this was, a volunteer group. It was through a working group that people were committing resource to, through their own organizations. So some preliminary work has been done here to do a basic reference architecture around the digital object framework. So looking at FAIR digital objects and what's needed for implementation of those. This needs to be extended, and it also needs to address the service angle. We also started a preliminary metadata mapping where we looked at the different kind of standards that are in place across the communities and the key standards for resource discovery. And I've done a mapping between those to start to think about a kind of minimal metadata model that can be used within EOSC. So within the interoperability framework, there are 4 layers that are addressed. And this takes its idea from the European interoperability framework, which was used for public resources. And it applies them to EOSC. So we address the legal interoperability, so thinking about the different legislative contexts in each of the member states and associated countries, and addressing issues of copyright and data protection and GDPR, and how we align those when there are differences across the different contexts. There's also a strong focus on licensing. Licenses are clearly critical for all of the digital objects, so we know who has permission to use those and under what restrictions. We then address organizational interoperability. So this is looking at aspects of governance and also the rules of participation. There are a set of rules of participation for EOSC at large that look at the requirements for the different service providers and also for the different users. And then the aspects that I think are of more interest to the audience today are semantic interoperability and the technical interoperability. So with semantic interoperability, there's a strong focus here on metadata and ontologies naturally, and interpreting the meaning of these. So understanding when people are using common terms, whether they do in fact mean the same thing, or if those terms are used in a different way in different contexts. With the technical interoperability, this is looking at the infrastructure at large and how we can interoperate between the different technical building blocks. So to give you a few example recommendations, we are calling for open specifications for all EOS services so that we know the regulations on those services and we can understand those. We call for coarse-grained and fine-grained data sets and other research object search tools, so people can search for a general topic, or they could search for a specific gene, for example, and find the relevant content. In order to deliver this, we do need clear, publicly available definitions for all concepts, metadata, and data schema. And we're trying to define this minimum metadata model and crosswalks to ease discovery over the federated data. Now, beyond that basic discovery layer, we do also need repositories of semantic artifacts, and we need to understand how these different ontologies are being governed and maintained and updated. And in terms of the licensing and the legal aspects, we call for standard human and machine readable licenses. We want permissive licenses, particularly for the metadata to aid the discovery, but ideally for the objects themselves as well. And in this context, CC0 is preferred over CC BY. So to dig in a little bit on the semantic interoperability implementation, there are a few layers to this. Obviously, we need the metadata catalog and the crosswalk so that we can have this common search. But we also need semantic artifact catalogs. We need to understand the different ontologies and what's meant by those different terms that are being used. And critical to this is the mapping repository so that we understand, one standard and how it aligns with another. Within the interoperability framework, there's a semantic use case that's presented, and I just wanted to provide that to you here. So a rare disease researcher, for example, is seeking clinical data, and they want to ensure that that data matches the current study population and the variables that are being interrogated. What they're trying to do is reach a population size that's needed, so increasing the size of the cohort. So they can search the metadata catalog to find candidate data sets, but then they need to go beyond that basic discovery layer, and they need to search semantic artifacts, which are based on the different domain metadata schema, to check whether the relevant variables are present, and if so, then they can include those in their search. So this is how they're agreeing a subset of data to reuse and to bring all that together within the EOS context. As I mentioned before, the FAIR and architecture working group started a basic metadata mapping. So this was looking at the common kind of discovery standards that are used, like Dublin Core, schema.org, DCAT, DDI, and they've proposed some mandatory and optional elements that can help us with FAIR digital objects. You can see the mandatory elements are very minimal here. So obviously we need persistent identifiers. We need the basic metadata that lets us know who's created the resource, what it is, when it was published, the resource type, and the licensing conditions, so we know how that can be reused. And then there are a number of optional elements as well. And one thing I'd like to stress here is that we're really focusing on developing crosswalks, not developing a new standard. We realize that there are lots of existing standards in use by the research communities, and we want to support their use within the EOS context. So really we need to map between them all rather than implementing anything new that adds a burden to the research groups. This was a key lesson from the EOS pilot project. They had tried to specify minimum information for EOS datasets, but there was quite a pushback from the community. Now, what we've done here, this mapping is very preliminary. This is not an end result. There needs to be a concerted piece of work to develop this further and to do a lot of consultation with the research communities. And that's something that will happen under the next round of EOS projects that are just getting started in the coming months. I did want to show one example of how this has already been done, though, on previous projects. The IVOA, the Virtual Observatory in Astronomy, has been integrated into the UDAP V2Find service. So what they've done is they've exposed their VO data using OAI PMH as a protocol to pull that out, and the Dublin Core standard, so that they were able to be integrated into this common search in V2Find, which is a kind of repository and discovery layer that UDAT offers. And then you can see there's various kind of keywords and publishers and resource types that are focused on the astronomy community. So there's a disciplinary extension to that metadata schema that's based on the astronomy standards and data. So this is the kind of model that needs to be taken further within EOSC to enable that kind of search and discovery that we're hoping for. So the next step then is implementing this into the EOSC portal. The portal is the main catalogue and marketplace where researchers can discover services and data sets. And we'll be taking all of the work that's gone on in previous projects and through the EOSC interoperability framework and implementing that within the portal. And the next project that's coming up, which will be addressing this, is EOSC Future. This is a multi-million euro investment with several partners. It brings together all of the e-infrastructures and the research infrastructures, and it will be addressing that discovery, but also the composability of resources. So enabling people to bring together all of the relevant data sets with the services they need to act on those. And there are different aspects of composability that will be addressed. It may be that, you know, a service provider wants to integrate with the common federated AAI to enable easy log-on to multiple services and not requiring researchers to use different mechanisms for access. Or what's of more interest is this kind of D arrow here, the composability and bringing together of data between different research clusters or communities. Now, this has happened within research clusters, that they've integrated data sets from different research fields, but cross-community is where we really need to enable that to address some of those societal challenges. So there are a number of science projects that will be worked on addressing key concerns like aging population, climate change, and smart cities, and the COVID pandemic. And that's where we'll be looking to enable that metadata exchange. Now, I mentioned this this project is still to begin, and I mentioned this now because within the EOS context, there's some basic discovery, but I think this ability to map between the different units and the values is a much bigger challenge, and it's something that really we're only just making a start on now. So that's a summary of what's been done within the EOS context and what's coming. Thank you very much for your attention.
Okay, thank you. So I hope all of you have a good time listening to the three very informative talk on various aspects of the global data science and efforts in the scientific community, as well as application domain expertise community in using description of units of measures in the various work in the various domains. Today in our discussion panel, we have Dr. Simon Cox again, one of the three speakers that you heard earlier on in the panel to answer some of your questions. And I believe you have posted some questions already on the chat board. So later on, Victoria will read some of them and post them to Simon for his enlightenment, to enlighten us, right? Of course, there's some question that you have posed that is for Eric as well as Sarah, but unfortunately, because of the time zone difference, they're not here, so they will not be able to answer those questions. But I believe Simon, being an expert data scientist in that field, he can help us in some of those questions, give us some perspective of some of those questions. So may I then have Victoria post some of the questions.
Thanks, Tom. And it's great to see some of the questions coming through. So the first question we received was from Jaria in NIMT, and she wants to know how the mapping between different systems is made. Is that you were talking about, Simon, in your presentation? Is that done using AI, or can you comment on that a bit further?
Yeah, I can comment on it a bit because I've done a lot of those mappings myself, and they've been done manually. It's sometimes tedious, sometimes there's a little bit of judgment involved. Over the last 3 months, I've probably done 2,000 or so, which is quite a lot to do manually, but is not impossible. I actually got a bit carried away with one of them. I thought there was only a few hundred, and once I got started, I discovered there was 1,500. But by then, I was already stuck in and couldn't do it programmatically. So, but that's okay. We're not talking large numbers here. This is not like big data. It's still a matter of just sitting down and we're doing a mapping between different systems, and so a lot of the work I was doing was just entering EUCOM codes for the various systems because those are good keys, and because I was already in the right headspace, I could do it quite rapidly.
So Simon, may I ask a follow-on question? I suppose if you look at the number of vocabularies and definitions, they are quite finite, but still can get into maybe the hundreds and maybe thousand. So in that case, doing it by hand and so on is somewhat manageable, right?
Yes.
But
that's very much the case I was trying to make at the end of my presentation. Is as long as we can keep the number of variant vocabularies and ontologies to 10 or fewer, then it's manageable. If it gets much bigger than that, it becomes very hard to manage.
Mm-hmm. So would it be correct for me to say that if the challenge is not maybe doing the ontology and mapping them, but the challenge is to harmonize maybe all the different definitions that is used by different domain experts?
I don't think that's the challenge. I think the definitions are really not very contentious. Everybody, we all understand the SI. We all understand, the underlying principles of metrology, even if there's some arguments about the details around the processes of calibrations and validations and these things, but that's not what I was talking about. So I actually don't think the ontologies are the challenge. I think the challenge more is to get the user community more broadly to understand that these systems exist and that they don't need to invent a new one. Because even in the last year, I've seen people saying, oh, I need a units of measure vocabulary, better build one of my own. And this is just ridiculous because this is not necessary. They're online, they have persistent web identifiers, they're available, there's no need to do a new one. And so my view is the challenge is not in the details, the internal details of the ontologies and the vocabularies, rather it's in the promulgation and the adoption of them more broadly.
Mm-hmm. But in terms of the software or the software tools that is being used to do some of this maybe machine actionable kind of metadata and so on, what are the common software tools we have now? Are there too many, or is it manageable?
I don't think there's too many. There's a few widely used libraries. In Python, there's a library called Pint, which does it quite nicely. There are the EUCOM online services hosted by the National Library of Medicine. They will do a quantity conversion convert the number in using one unit of measurement into the number representing the same quantity, but using a different unit of measurement. There's other Java libraries around. I don't think these are the problem. More, it's just there are subtle differences between the codes used in some of these systems, and which means there's clashes. If you use the wrong ones, there may be some ambiguity. This is why I particularly like the UCOM system, because that one has really flushed out all of the ambiguities. And really is, even though it comes strictly from the clinical medical background, nevertheless it's a fully general system which has got good codes. So I would not like us to imagine problems where they're not big problems. My view is the biggest problem is the social problem, actually, is getting communities to recognize and understand that this is essentially a solved problem. There is a small number of choices already available. If you adopt one of those, you will be interoperable.
Okay, thank you.
Another question, just quickly, while we're on the subject of mapping, which has come through from Daniel. Simon, how do we verify that the mappings that you do are correct? Is there any method for review that you recommend?
Well, all of the mappings that I've done have then been reviewed by the custodians of the systems which I've submitted them to. I've done mappings for basically the ones that were in my presentation, the NERC one, the QUDT, the OM, the suite, and in none of these cases can I just push changes into a code repository. They all have to be reviewed. Now, are those reviews sufficient? This is hard to be absolutely definitive about, but I suppose I would say I'm respecting the governance process of the vocabularies, the governance processes of the inventories and the systems. Those governance processes are the processes which the communities which manage those consider are adequate. And it's not really my job to challenge that. With all of these systems, there is a governance process which ultimately depends on some people, even if it's people writing some software to do the checking. There will, I certainly won't say that there aren't potentially errors in some of the things that I have submitted, but I would say they've all been reviewed, and in most cases by 2 or 3 separate sets of eyes before they get accepted into adopted into any of one of those systems. And this is basic good software engineering practice these days. Where might be the risks? The risks of getting things wrong might be if some of the numbers were wrong, of the conversion factors or whatever. Well, I haven't even dealt with those. Okay, the mappings that I've just done have said this one from this system corresponds with that one from that system. Haven't touched any of the conversion factors. Whatever they are in the different systems remain what they were. It's just there is so the changes or the modifications or the alignments that we've been contributing probably weren't looking at spaces where there was a risk of breaking some system numerically, if you like.
Thanks, Simon. Another question through from Blair Hall at MSL is, if we already have enough ontologies, what does the SI need to do to become more digitally user-friendly? Are there aspects of the current SI brochure that need to be considered now in the light of digital transformation ambitions on the part of the community?
Yeah, that's a good question. Thanks, Blair, for hearing my premise that we already have enough ontologies. the thing which I find problematic in the current SI brochure is that it's only designed for human consumption. It's not designed for, none of the definitions in the SI brochure, to my knowledge anyway, are provided in a form which is machine actionable. So they can't be used directly to configure a system. So I would say that now, I have a background in web technology, and one of the things that we have in the web is the possibility of a single web identifier being able to get alternative representations of something, a representation available for a human, but then also a representation available for a machine, and it's all done by tweaking the headers in the request. And the details of that are important to people who are building systems and not important to metrologists. And that's, if you like, the challenge is that as long as the SI brochure is published by people, which is appropriate, is published by metrologists, it needs to be supplemented, I think, by some additional resources being available when people request using the same web identifier, but say, I don't want to see it as a web page. I want to see it as a QUDT representation, or as an OM representation, or as a UO representation, or as a suite representation. And there's mechanisms to do this, standard web mechanisms to do this, and it just say, therefore, a brochure becomes a whole lot more useful because it's machine actionable.
Great. Another question from Katsuhiro Shirono. If we choose only one existing digital expression system, what do you think is the most promising in metrology?
I think there's little flaws in all of them. The one I'm most used to working with is QUDT, but in order to express the conversions that you would want to do, you need to traverse several steps in a graph using the QUDT representation, whereas the OM representation is a bit more direct. But the OM representation, in my view, is not as well governed because there's basically just one gatekeeper there, whereas with QUDT there's 3 or 4 people checking all the time. So, but it's not really a beauty contest, and it's not that important between those because they all contain in the end the same information. It's just the path to get to it is a little more tortuous in QUDT, but the governance process in OM is not so good. There's some new work kicking off in the OBO Foundry to revive the UO ontology, and I know the people who are working on that, and that may turn out to be good. But there's a mixture of concerns here. There's the technical precision part, but then it would be a mistake to overlook or neglect the governance behind it. QUDT is really good because you can get new units added in a few days and a release every month. Okay, and that's important for some communities. If they need it now, then if you can't give it to them now, that's when they go off and do their own thing. And so if we want to keep people in the fold and to discourage people from forking and developing new systems, then it means we have to manage our systems in a way which is responsive to the broad community's needs. But having said that, QUDT is run by some retired old geezers who happen to have time on their hands. Okay. And is that the ideal platform for international research and science and technology and engineering? Of course not. So it's something which perhaps the BIPM and the SI system needs to look at, or some of the institutes like NIST and such like need to think about whether there needs to be a constant level of funding for somebody to manage that maintenance process. So it's, and my interest in this space has is in a sense is surprising because I'm a domain scientist. And so why am I working on this very, very general part of the problem? Well, it's because nobody else is. Fortunately, my employer tolerates me wasting some time. I'm sorry, spending some time on this. Um, but generally you need a big organization which can hide a little bit of this work off in the corners, or you need a bunch of retired geezers who haven't got anything better to do.
Yeah.
So Simon, may I ask a follow-up questions? You have described to us some of the useful work that retirees and people who have time have done so much for the community, right? So looking at it, because if it's such a important, so-called piece of work and infrastructure, who do you think should be, the people who should be managing this kind of infrastructure for the global community? I mean, like, for example, in the case of metrology, we have NMIs that, propagate the SI units all over the world, and each of the country, put in resources to maintain physical standards for calibration and measurement and methods and so on, right? So in the equivalent in this space, who do you think should be the guardian of such kind of, capabilities?
I agree. I think the NMIs is a good place to look because those are operating organizations with real budgets and distributed and I think would I don't fully understand how NMIs generally are funded, but like I was sort of saying, you need an organization that can essentially take a small tax off their general operating, 5%, 2%, I don't know, something which is enough to support, 2 or 3 people, part-time if necessary, but who have this as a responsibility. And I, behind in the beginning of your question, Thomas, you're saying this is important. So why are we relying on a bunch of retired geezers to do it out of the goodness of their heart? Now, some cases there's a very good reason because they're very experienced, because they've been involved in it for a long time, and maybe they have some time on their hands now, but that's not a sustainable business model going forward. And I standards in general is a difficult business model. ISO, the standards organization, gets a lot of resentment for the fact they charge so much for their standards. But that's their model for how they fund their editors and their publication platform. It doesn't seem to be the right one for something as important as units of measure, which everyone needs to use, or things go wrong. Yeah.
So a quick follow-up question again. You mentioned about the QEDT suite and UCOM and that there's web services that can translate units in these different systems and so on, but in a maybe more typical general setting like the national measurement institutes in the region and so on. Today, typically, you also mentioned, you need 2 or 3 part-time people who can work on this. So I think today we are typically not set up with people who know data science, who know, the IT part of the equation. So how do you think we should resource NMIs to be able to do this?
Well, the thing I'm talking about here, of course, is a fully international, fully general system, and NMIs are mostly constituted as national organizations. So you'd be looking for somehow either a setting up a small organization which is funded jointly by all of the NMIs or through whatever systems that the the international metrology community funds its collaborations, or you delegate it to one of the NMIs to manage it on behalf of everybody else, or something like that. I'm not an organization builder or leader or whatever. So exactly the details of how one might constitute this, I'm not sure. But it's I don't think the investment needs to be that large, but it does need to be, if you like, guaranteed. And that's it really needs to be understood that this should be a small tax. And Thomas, your point there, which is it needs metrologists on hand to consult with, but primarily it's a governance and technology job to keep these things ticking over. I'm not a metrologist. I'm a bit of a scientist and a bit of a computer scientist, but and only by osmosis to a certain extent. I have a PhD in geophysics, but that was a long, long time ago. So the skill set here is largely technical, but also the skills to know, I don't understand this, and to have the list of people to ask, the metrology community, what's the answer to this one? So if you think that we can follow up on these proposals, in a concrete way and say, right, we need to establish an organization to assist the IPM or to separately govern one of these existing systems to allow them to support the community, then then let's talk. I'm not sure we're going to complete it in the context of this live session we're running now, and I'm the only panelist.
Yeah. And I suppose one way to do it is like what you have done: reinvent yourself and learn to be a data scientist for some of the people who have that kind of interest.
Yeah, exactly.
Yeah, but I think other than doing something for the community, I think the NMIs may at some point also digitalize their services, and when they digitalize the services, they probably would need some number of skilled people who can help maintain the local services, right?
Yes, absolutely. And it's a complementary skill set to the metrologists, who are the main people of course, and totally they should be the main people who are in the NMIs, their metrology institutes.
Okay, so I think we had a very good conversation with Simon. Thank you very much for answering all the questions that are, for the whole sessions.
Yes.
And I think we got quite a bit of insight as to maybe what as NMI we can do, and as the community we should do and can do together. So thank you very much for your time, and thank you very much everyone for listening in. So we are coming to the end of this Q&A session. We will take a break. We'll come back maybe in, instead of 30 minutes, can we come back in 25 minutes? Okay.
Okay.
Thank you. So we'll see you again for topic 2 later on in 25 minutes. Okay.
Thank you.
Bye.